Hello, everybody, and welcome to MME 3413 Materials Characterization. I'm your instructor, Dr. Dave Robertson, and before we get too far into the class, I wanted to start off by taking a look at this micrograph. And so take a look at this micrograph. Ask yourself some questions. And one question to ask is, how is this material processed? Okay, so how was this thing made? What is the material made out of? Okay, is it wood? Is it metal? Is it glass? Who knows, right? So ask yourself, what is this made out of? And another thing you probably want to ask yourself is what could be added to this image to make the image better, to give us more information to help us interpret the image. And three, what instrument was, or four, probably four, lost count. What instrument was used to make this micrograph? Okay, was it an optical microscope? Was it a scanning electron microscope? Could it have possibly been an atomic force microscope? So ask yourself these questions. And before we answer these questions, I have another activity I would like you to do. So keep watching. Hi, everybody, and welcome to Microstructural and Microchemical Characterization. Before we get too far into it, go and find something in your house, whatever it is, preferably a single object, nothing too complex. It has a lot of parts. I picked this metal object I found in my garage, and I wanted to go through a quick exercise before we get way into the class. So go ahead and hit pause now and go get your object. And assuming you hit pause and you've come back, I'm going to take a look at this object, and you can take a look at your object at the same time with me. And a couple of things I want you to do. I want you to take a look at it, and using only what you see with your eyes and what you can feel with your hands, try to figure out what your object is made out of and how it was made. And so if you look at my object, I know it's metal. I know it's metal because it feels kind of heavy. If I shine it, in the light a certain way, you get some sort of luster. So we're taught at a very young age that metals have a luster. Beyond that, I don't actually know what kind of metal it is. Okay, so I've reached a limit at figuring out what this is made out of. Sometimes if you have something made out of aluminum, you could maybe say, hey, this is aluminum. I know because it's really light or something like that. This is pretty heavy. I'm not quite sure. Maybe it's copper based on the color. How it's made is another question. So let's see if we can get this on the camera. If you look closely, you see there's kind of a line which maybe is there because of two parts of a mold. So I could perhaps say this was made with injection molding. Maybe it was made with sand casting. But I get to a point where I'm limited with what I can tell about an object based on just my eyes and my hands. But it's also very powerful. Your sight and your hands can tell you a lot. So I know this is a little bit rough. Maybe that leads me to believe this was sand cast versus injection molding. So I'm using some experience too when I'm doing my kind of off-the-shelf characterization, so to speak. So things you want to kind of take home from this. One, you're extremely limited by what you can tell about a material from your eyes and your hands, which is why we use the instrumentation that we'll talk about in this class. However, though, your eyes and your hands are also very powerful because we use particularly our eyes to interpret the data we get off the instrumentation. The other thing that you want to kind of take home from this exercise is experience counts for a lot. And so we're lucky enough as a department to have someone like Dr. Stafford who has a boatload of experience in failure analysis. I'm a bit younger, but I have a lot of experience in materials characterization as well and materials processing. But experience does count for a lot. The other thing to take into account and also think about the TED Talk that you guys were assigned to watch is a microscopy is a very powerful tool, and also characterization in general, whether it's spectroscopy, are also very powerful tools. And they're the tools we use pretty much on a daily basis as material scientists and engineers. So when you think about this class, think about what you're using as the probe. And so when we look at our object, our probe is our eyes and our hands. In class, we use photons and electrons primarily, and the way these photons and electrons interact with the material gives us the information we need to solve whatever material problem we're dealing with. So thank you very much for your time. All right, so looking at this micrograph, one thing that could make it better was one of the questions that was asked. Is very, very important, and hopefully by this stage in your academic career, it jumped right out at you. And dimensional reference, we need some sort of marker to tell us how big the features are. And that kind of gives you a lot of clues. One thing that I will kind of say is experience plays a big role in the interpretation of micrographs. And one of the features that really kind of jumps out at me, and let me laser pointer it up here, is these facets. And these facets are representative of, are indicative actually, representative is the wrong word, indicative of solid state grain growth. And so we know that there's some growth fronts that occurred. And solid state grain growth is seen primarily in metals and ceramics, and particularly during a sintering process, so I can get some idea of how this material was processed by the presence of these facets. And so if you just handed me this micrograph, I would say, well, this is either ceramic or metal, but I can tell you it was sintered. No melting occurred here because of the solid state grain growth. And we also see a lot of grain boundaries. And so there's some triple points here. So that's really kind of cool, grain boundary triple points. And they're almost in the kind of classical depiction of a grain boundary where you see kind of this honeycomb structure start to form, because that's the lowest surface energy configuration that grains can really achieve. We see some pores here, so I can tell you that it wasn't pressure assisted sintering because we have some pores, we have some empty voids. If you asked me what made it, I would just guess an SEM. And if you asked me why, I would probably say, well, I really like SEMs. And what else? What's it made out of? Metals or ceramics? What can make it better? Using a dimensional reference, what instrument made it? I would guess SEM. It could potentially be an optical microscope as well, but probably an SEM. And the reason why I would say SEM is I see kind of these shadings here, like these kind of bright areas, and that's more consistent with electron emission. So again, some experience coming into play in the interpretation of this micrograph. I think I answered all the questions. I probably should have written them down, but two key things to take away. Experience plays a big role in how you interpret this stuff. And two, always have a dimensional reference. Always have a dimensional reference. This class is pretty much teaching us how to gather information and also interpret the information. So we want to know what we're looking at is made out of, things like what are the grain size. We want to answer questions like what did process X do to the material. We do failure analysis quite a bit in our department, so we want to know what can the fracture surface tell us about how the component failed. If we're dealing with new material systems, what is the lattice parameter? What phases are present? That's also a very big deal to a lot of us. What is the crystallographic orientation? That can tie directly into how the material was processed, and how much of element X is present in our material. So these are just pretty common questions that material scientists like us ask ourselves when we're analyzing a material. One thing, so kind of based on the activity we did earlier, I want you to kind of think about this, because the eye is very powerful in telling us stuff. The way we touch is also a very powerful tool, and hopefully you participated in that activity and you kind of got a feel of it. But we're limited with what we can see. And so I always ask students this: what you think the smallest feature is that your eye can resolve. And we'll talk a little bit about the difference between resolution and magnification, that kind of thing, as the course progresses. So we'll give a couple of seconds. What do you think the smallest feature is that your eye can resolve? It's roughly between 1 micron and 1 millimeter, so I'm kind of punting a little bit. I would say 250 to 500 microns is roughly the limit of the unaided eye. One thing to kind of point out, this region here, kind of between the millimeter and the micron, is sometimes called the mesoscale. Other people will blatantly attest that the mesoscale is between 1 nanometer and 1 micron. But it's an in-between resolution. So meso means in between. We see some common things that we come across in our life, and this slide's a little bit dated. We have an iPod on here, so I'm a tad embarrassed. Maybe I should update it. But there's different scales, okay? So an airport runway can be on the kilometer range. An atom is actually on the angstrom range, so pretty small. I share this story quite often when I teach this course. When I was a young lad, we didn't really do things in terms of nanometers. We did things in terms of angstrom. And I've added in angstrom to this slide. Everything here was in terms of nanometers. I kind of wanted to kind of pay homage. When we deal with X-ray diffraction, we deal a lot with angstroms. But anyway, just to kind of give you a relative size difference with what we deal with. In the material world, in a lot of cases, we deal in this region here, the kind of the micron to angstrom range. We're doing some more macro stuff, work on the millimeter range. Seldomly, as material scientists, do we work with characterization on things of the meter or kilometer range. So just kind of putting this context out there. We deal with different scales in the material science world because it gives us different types of information. And so here we have a characterized piece of material. This is cobalt chromoly, and this was formed via additive manufacturing. So this cube here, we have, I call it a metallography cube. Somebody kind of gave it a curve, so it's not quite a cube. But for metallography, you can tell only so much, okay? And metallography, very powerful tool. I'm not discrediting it, but you get to a limit as well. So just as we get to a limit with our eye, we also get to a limit with what we can tell by optical microscopy as well. But we can tell some powerful stuff. So this arrow tells us that it was built in this direction. So that's what that arrow is telling us. Built with an additive manufacturing process. What the additive manufacturing process does to the microstructure is it kind of columnates the precipitates, but we can't tell much about the morphology of the precipitates themselves. And if you look at the scale bar, this scale bar of 15 microns corresponds to this micrograph. On the other hand, we have this cube with the corresponding same faces, and this was made with a transmission electron microscope. Now, TEMs can go all the way up to the atomic scale, so we can see individual atoms with a TEM. This is a little bit lower mag, but it's still a TEM, and we're still able to get a higher magnification than we could get with optical microscopy. And the magnification here, this scale bar, very small, corresponds to 200 microns, okay? So we have an order of magnitude difference roughly, maybe a little bit more if we compare the size of the scale bar. So we're getting different information from the TEM. And what this TEM is telling us is that the morphology of these precipitates is cubic in nature. And you can kind of see a nice little square there. So different scales give us different information. Kind of some terms that we deal with. So macrostructure is detectable by common methods of non-destructive evaluation. So that would be a large pore. I still have my object that I use for my activity, and hopefully you can see it in my little camera square. But here, I saw this parting line, so that would be a macrostructure. Mesostructure, so features which are on the borderline of the visible. Gas bubbles would be one. maybe even grains, depending on the grain size. There are situations where, especially if you're looking at a cast billet, the grain structure is on the macro scale. So there are some gray areas when we talk about this terminology. Microstructure is a structural phenomena. So grain size is a real big one. Grain morphology, how the grains look, are they elongated, are they equiaxed? That's another thing that we care about. And nanostructure, so submicron features such as the lattice structure. And we typically get that off of TEM or XRD. So trying not to ramble on too much, but we have macrostructure, mesostructure, microstructure, and nanostructure. So kind of 4 different scales that we're kind of dealing with. Different scales require different tools, and so scratches could be 10 times the human eye, which you can see with the human eye. Grain size or microstructure, a higher power, and grain boundaries, dislocations, and lattice structure, you can kind of see the exponent kind of getting bigger and bigger and bigger. So how much power we need. So to see a scratch, we could probably see it with our eyes, but maybe we need something with a 10x mag to really characterize the scratch. Grain size, microstructure, optical microscopy, typically 100 times that of your eye. Grain boundaries to actually characterize the boundary, so 1,000 times minimum. Dislocations, you need 10,000 times and greater, and lattice structure even greater. And the tools we use the tools we use to get this level of magnification, an example here. So these are just examples. There's a bunch of other things you could probably use to see a scratch, but a magnifying lens, simple magnifying lens, you can see a scratch. Optical microscope for grain size. Grain boundaries, you can characterize with the TEM. Dislocations, you definitely need a TEM. Don't ever let anyone tell you different. Lattice structure, TEM, and also an X-ray diffractometer. And the wavelength of the probe is decreasing with every instrument as we're kind of going down on this slide. So the wavelength is decreasing as we go down. So we mostly glean qualitative data from this, but you can glean quantitative data from this. So let's just take the example of an optical micrograph. You can get grain size from that. Okay, so you can tell qualitatively, let's just say it's an equiax grain structure. So qualitatively, the grain structure is equiaxed, or perhaps it's elongated, columnar. Okay, that's qualitative data. But if we actually measure the grain size, we can get quantitative data. So you have to do a little bit of work most times to get quantitative data. The qualitative data generally comes from just looking at it. And that goes for XRD as well. So if we look at a spectra, we can tell if we have more phase as compared to another by the intensity of the peak. And I'm sorry I'm not showing examples of this. I'm kind of verbose today. But we'll see examples of this in depth as the course progresses. This is just an intro. The smallest imageable objects. This is really cool. I'm always really fascinated. And so if you have gotten a hold of the book, check out page 16. I'm always extremely fascinated with the history of how the instruments we use as material scientists and engineers were developed. This is a field ion microscope, and this microscope gave rise to more advanced microscopes such as an atomic force microscope and a scanning tunneling microscope. But it all started here, and people making a very, very thin tip, and they actually imaged the tip itself, and it's tungsten. And so ask yourself this: why do I see a bunch of circles? Okay, think about it a little bit. All right, so hopefully you've thought about it. The atoms are actually moving, and they have a circular motion when they're moving. And we see that here on this fluorescent screen. Ask yourself the crystal structure of tungsten, and maybe it answers some questions. This is a little ambiguous, I know. This looks like some sort of a monochromatic tie-dye. But the crystal structure of tungsten is body-centered cubic, and you can almost visualize BCC when you look at this. micrograph, if you will. Other things that we find ourselves concerned with as material scientists are the composition and where. Is there a diffusion zone? These kind of questions are what we want to ask ourselves. So discrete chemical analysis, bulk chemical analysis, and surface chemical analysis are three types of chemistry analyses, if you will, that we will perform or we perform as material scientists and engineers. So discrete chemical analysis is EDS. That's a very, very common one. Sometimes people call EDS EDX. I always trip out on that. I don't know why. Bulk chemical analysis, OES, and the ever popular XRF, so optical emission spectroscopy and X-ray fluorescence, and surface chemical analysis, Auger analysis, not Auger, Auger analysis. And that's purely quantitative data. So here we have a tin bismuth solder, and we kind of over-etched it, I know, but we took discrete chemical analysis. This is an example of EDS. We took discrete chemical analysis from the two phases, and we found that one of the phases is bismuth-rich, and the other phase is composed of tin and bismuth. So that's kind of cool. So little things like this are what we can do with the tools when we combine the information from different characterization tools together. It becomes very, very powerful, and we can do big things like failure analysis, process characterization, write our theses and dissertations. Very important stuff that we do in life. Still kind of giving the overview of the class. So this class is pretty much designed to give us the skills and tools that we need to do our jobs as engineers, particularly materials engineers. And here's kind of another example. You guys probably see this a lot in failure analysis. This would be the failure analysis of a polymer, kind of something very near and dear to my heart. And so we see our mirror, mist, and Hackle zone, the SEM. When we talk about SEM, I always ask this question if it is the most versatile tool that we use as material scientists and engineers. So very excited. Hopefully this is whetting your appetite for the course, and we have a good time. So thank you very much for your time. Think I cut off myself too early. I must have added this before I rehearsed. A big thing about this is particle material interaction. So a big thing, the activity we did dealt with your eyes and your hands as probes. I said this, that most of the materials we use are photons, or deal with photons and electrons. I think I need to rephrase that. Most of the tools we use utilize either photons or electrons or both to interact with the material and then give us the information we need. The interaction of photons and electrons with the material is classified in two big categories. So elastic scattering and inelastic scattering. So elastic scattering, optical imaging, so the light bouncing off an object and then we see it, whether it's an etched microstructure or if it's just telling if something's white or blue, that's elastic scattering. Diffraction would be an example of an elastic process. In scanning electron microscopy, we deal with two different flavors of electrons. Secondary electrons and backscattered electrons. And secondary electrons actually do something to the material. So that's inelastic. So I'm kind of doing a segue from elastic to inelastic. Backscattered electrons do nothing to the material. They go into the material, go around the nucleus of the atoms, and come back out. So that's elastic scattering. Inelastic scattering, secondary electrons, we'll talk very deeply about the generation of backscattered and secondary electrons as this class progresses, but that's an inelastic scattering process. And EDS spectra, which is X-rays basically, the generation of X-rays is also an inelastic scattering process. Kind of my fancy animation. Photons or electrons are both interact with material. That interaction gives us information, important information. Here's combining elastic and inelastic scattering. So this is a secondary, excuse me, I am very remiss. It even tells me right here, backscatter electron. This is a backscatter electron micrograph. Backscatter electrons give us elemental contrast, and so the brighter one is a higher Z number. So we'll get into that in a little more detail. But these are X-ray maps surrounding it. So it tells you which element is living where on the micrograph, basically. And X-rays are an inelastic process. So we have an elastic electron image and an inelastic X-ray map. So you can use elastic and inelastic interactions at the same time to get the information you want. This is from the book, so get a hold of the book, read chapter 1. It's very good. Some examples of kind of what I've talked about in the past, basically, or earlier in this presentation. So elastic scattering, inelastic scattering, a little bit more in depth. So we're talking about reciprocal and real space, and we'll talk about that in a lot more detail later on in class. Inelastic scattering, energy loss, that kind of thing. We're not doing anything to we are doing something to the material, excuse me. I get it confused, so hopefully you don't get it confused. One thing that I want to talk about now rather than later is the difference in black and white is a huge, huge tool. And I guess in the most simplest form, kind of pause there, my brain kind of told me I had enough. The simplest definition of contrast is literally the difference between black and white. And when we look at most of these micrographs, they're black and white images, except for when we artificially color them. But usually when we're looking at a micrograph, whether it's an optical micrograph, a scanning electron micrograph, or a transmission electron micrograph, we're learning about the material or interpreting the results by basically looking at the difference in black and white. So I made this slide. Contrast is a big, big, big factor. Okay, so a lot of this class, and it's funny when you think about it, but in the simplest form or simplest definition, a lot of this class is telling the difference between black and white and interpreting something based on lines on a screen, which is spectra. And you'll see more what I mean as this class progresses. Wavelength determines resolution, and that's a huge, huge thing. So visible light is roughly 0.56 microns. The wavelength of the electron, which is defined by de Broglie, kind of the essence of, or beginnings of quantum physics, if you will, is pretty small, 0.037 nanometers, and that's just one. We'll see later on that the wavelength is basically dictated by accelerating voltage, so we'll talk about that a little bit later. Copper K alpha, so I'll pause a little bit here or spend a little bit more time. Copper K alpha is an X-ray, and it's a very common X-ray used on X-ray diffractometers, or wavelength used on X-ray diffractometers, and it happens to be the wavelength of our X-ray diffractometers here in metallurgy. And so copper K alpha, we'll learn a lot more about what all this means when we talk about X-ray diffractometry, but the wavelength of the X-rays in our X-ray diffractometers are 1.54 angstroms. I don't know why I put it in nanometers after I went off so long about how the angstrom was what I used as a lad. But anyway, 0.154 nanometers or 1.54 angstroms. All right, so now hopefully this whets your appetite for the course, and hopefully we have a good time. So thank you very much, you guys, for your time. And if you have any questions, feel free to email me. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.